Hello everyone. You'll often see the resolution numbers given in terms of a velocity over square root of hertz. Now, how do you make sense of it? Meaning, what does it mean in terms of time domain or frequency domain? What does it mean in terms of actual velocity or displacement? That's what we want to go through. So let's start off with an example here. So this is one of the decoders in one of our systems, so 1 mm per second may be the range, or 2 or 3. So now let's consider 1 mm per second. A couple of important things. 0 to 100 kilohertz is the bandwidth for this particular range. And these are the numbers you'll see on the bottom is the resolution numbers. There's a range going from what the resolution is at 0 to what the resolution is at 100 kilohertz. And you'll see numbers like these, nanometers per seconds per square root hertz. But what does it mean in terms of velocity or displacement? What does it mean in terms of frequency or time? So these are the 4 cases we want to consider. Now, let's start off with some explanation as to how do you, if you have a frequency of interest, you only have 2 numbers. So you kind of basically just extrapolate what it would be at a certain frequency. So let's say I want to know what's at 65 kilohertz. You can kind of guess that, okay, it's about 10 nanometers per second per square root hertz. Let's take that as an example and look at it. So at 65 kilohertz, my resolution that is in the manual is 10 nanometers per second per square root hertz. In frequency domain, the most important portion is the FFT resolution, and this comes from the number of FFT lines. So you have to keep this in mind, and you basically take the square root of hertz, square root of this number, whatever this frequency resolution is for your case, and multiply the resolution number by this number, and that's how you get your pure velocity number. Now you take this velocity number, this corresponds to what it is at this particular frequency. If you want to do displacement, you basically take this number and divide it by 2 pi f, f again being the frequency of interest. So you can see that the velocity resolution would depend on the frequency of interest, and it would also depend on your FFT resolution. The finer the resolution, your noise is more distributed, it's going to be lower. So this is how you would deal with velocity or displacement in frequency domain. Now let's look at velocity or displacement in time domain. In time domain, you have to consider the entire resolution number, meaning you're not now distributing the load or the noise in these individual bins. So here, if my bandwidth is 100 kilohertz, you will take this entire number in your calculation. So again, you'll take 15 nanometers per second per square root hertz and then multiply it by the entire bandwidth. Now, this is at 100 kilohertz. You have to keep in mind that if your interest is in, if you're restricting your data acquisition for a smaller number, let's say 20 kilohertz, that's the number you would use here. Once you have the number for the velocity resolution, the process is the same. You divide it by 2 pi f to get to your displacement number. So I hope this helps how you would deal with it in frequency domain and how you would deal with it in time domain. Thank you.